My name is Eli, and I'm from the New Jersey Institute of Technology. I want to introduce my supervisor, Dr. Shaohua Wang, which has a cooperation with me on this research topic. And also, there are two great team members in our group, Dr. Tien Nguyen and his students on Nguyen. They all from the University of Texas at Dallas. So today our topic is the improving bug detection with context-based code representation learning and attention-based neural networks. So before talking to you about our approach, I would like to talk a little bit about automatic bug detection. In the software development process, bug detection has become more important to help developers to find bugs and improve their efficiency. And there are several state-of-art automated bug detection approaches. There are mainly three types. The first type is rule-based bug detection approaches. For example, the finding bugs. But this type of approaches has a limitation that when there comes new type of bugs, the developers need to define the new rules to detect this new kind of bugs. And for the second type of the bug detection is the mining-based bug detection approaches. For example, the NAR miner, which is a very recent study. And the limitation of this type is that this kind of approaches cannot distinguish the bugs in some infrequent code snippet and situation. So sometimes they often have a very high false positive when you're running this kind of tools. And then the third type is the machine learning based bug detection. Also have an example, which is the deep bug. I think this model is very well known in this area. And the limitation of this type of bug detection approaches is that they cannot detect the bugs involved in several methods. They only consider the bug inside of one method. They do not consider the relationship. And for example, here example showing that why this type of approaches cannot work well in some situation. In this example, you can see that in method 1, they have a method called to method 2 and also to method 3. And the method 3 has a bug on the line 2 that means the 2 lowercase. They have this bug because in method 2, the line 2, they have a failed dot to lowercase. So if you only consider the buggy line in method 3, which is this line, you cannot find how to fix this bug, or you don't know whether it is buggy or not. So with the limitation and this example, we can see that the bug detection should consider dependent method, not only the single method. So based on this, we have some key ideas for our approach. So the first idea is that we want to get as more as possible information from the code. So firstly, we extract the information from the local context, which here means the code content and the code structure inside of the method. And also, we want to consider the global context, which is the relationship between different methods. So here, we want to consider both the data dependencies and the control dependence, so among these statements. And also, because our approach is for the bug detection, we want to specialize our code representation ways. So we want to add a trainable weight on the buggy position when we're doing the training. So based on these key ideas, we come up with our whole approach. It looks like a little bit complex, but I will explain one by one. So at first, we will do the pre-process. We transfer each Java method inside of the incoming Java project into the AST trace, and then we have a list of AST trace. After having this, we come up to our first step, which is the attention-based local context representation learning. In this step, it mainly have 4 small sections. It looks like a little bit complex, but I can explain it a little bit easier. So firstly, we extract the long path, which is used to represent the AST tree. The long path here means the path starts from a leaf node of the AST tree and going up to the root node and going down to the other leaf node. We use the greedy strategy to extract minimum number of long passes to cover all nodes inside of AST tree. So we use long passes instead of AST tree to represent the whole method. With this long pass, we can learn the AST node representation. It's quite simple. We just regard the whole long pass as sequence, each node as a word, and then we can use word to act on that. It's really simple. And with the representation vector list, we can learn the local context representation from this. Firstly, if this path is buggy when doing the training, we add a trainable weight on this one. And then we put the vector we get to the attention-based RN and CN to train the results. We use RNN here because we think in the long pass, it's more like a sequence. We can get a structure of the code. And for CNN here, we use it because the CNN is good at extract the relationship at the SCAP space, which means if the first token and the fifth token has a bug, they can have extract the relationship between them. So after having these two kinds of representation ways, we use the multi-head attention to combine these two representation ways together to get the pass local context vectors. After have the local context, I will talk about how we get a global context, which is the second step. It's a network-based global context representation learning. In this step, because we want to get global context, we need to consider using the graphs. So we try several graphs, but finally we choose the program dependency graph and data flow graph. These two graphs, we use the existing tools to generate. And then after generating these two graphs, we come up with the way of getting the representation to change the graph to the representation vectors. We use node to vec in this step to represent each node on these two graphs. In this way, we have two lists of representation vectors, one for PEG, one for the DFG. And then because in PEG and DFG, each node is a statement, so if we want to get the global context for the long pass, we need to find a way to do that. For here, we just simply average all the related pass vectors and then combine them together, get average to get a global context representation vector for each long pass. And with the local context and the global context we get from these two steps, we use the matrix multiplication to put them together to get a final representation vector for this long pass. And as I said, in each method, we want to use the long passes instead of AST to represent it. So when we have the long passes, we firstly combine all this long passes representation vector together, which become a matrix. Then we can simply use the SCM model to do the classification. With the classification, we can know which of them are buggy, which of them are not. So this is the whole steps of how our model works. The important thing is that we want to evaluate if our idea can work or not. So we come up with 3 research questions in empirical evaluation. The first research question is that we want to compare our approach with other bug detection approaches to see if our approach can work or not. These baselines include the deep bugs, bug ramming, minor and fun bugs. These 4 different baselines include all 3 types bug detection approaches I mentioned at the beginning. And then I also want to compare with our code representation ways with other code representation because, as I said, I specialize our code representation for bug detection. So I want to see if this specialized is useful or not. So we compare with these baselines listed here. We only consider the code representation part for this approach. We do not consider the whole model because it's unfair. And then at the end, we want to do a sensitivity analysis to see each factor of our model influence the final performance of our approach. And to do the experiment, we collect data from 8 well-known large open source Java projects with 92 versions in total and over 4.9 million of Java methods. And the data here listed in the table, you can have a look. And with this data, we come up with some results for all these research questions. For the first research question, we firstly get a result for the cross-project setting. The cross-project means we only use one project to do the test, and we use the rest, all other 7 projects to do the training. So from the graph, we can see that our approach have a big increase on the F score. We mainly compare the F score in here in the evaluation part. The conclusion is that we can have an improvement up to 257 on F1 score when compared with other things on the cross-project setting. And also, we do the cross-version testing for the same research question. The cross-version means that we use the newest version of one project to do the testing, but the previous version and other project to do the training. So we want to see if the previous version can provide useful information on the newest version to do the bug detection. So here we also have a great outperform than comparing with other baselines. So we have a relevant improve up to 156 improve on the F1 score and in the cross-version setting. And to analysis in more detailed space, we do overlap analysis. The overlap analysis showing that the green part is the blue part is our approach, and the other color is the other baselines. So the covered part is that the bugs that both of us can detect. From this graph, we can see that our approach can detect at least 23 unique bugs when comparing with other baselines, which is much more than other 4 baselines. This result is reported on the top 100 bugs because each bug detection approaches can report a list of bugs with the possibility of to be bugged or not. So we only picked the top 100, and among them, our approach can have 48 true bugs, which means we detect correctly for 48 true bugs. And then we come up with the conclusion that our approach can do better on the bug detection problem when comparing with other state-of-art approaches. And then in the second research question, we want to compare our approach with other code representation approaches only on the code representation section. We also do the cross-project setting first. The result shows that our approach can have a relevant improvement over other representation ways, up to 206 in accuracy in cross-project setting. And in the cross-version setting, our approach can increase up to 206 in accuracy in cross-version setting. So from these two things, it's showing that our specialize on the code representation is useful in the bug detection problem. And the overlapping analysis also shows the result like this. From the result, you can see it's similar as the research question 1. Our approach can detect at least 21 unique bugs, while other baselines can only detect at least 7. So it's much more than them. So which means our code representation way is really good on the bug detection problem. And then the third research question is that we want to do a sensitivity analysis. We split our whole model into mainly 4 parts. The first part is local context. The second part is global context, include the program dependency graph and data flow graph. And the third part is the multi-head attention. I just use attention here to replace it. Then we come up with this table. From this table, we can say that by adding each section into the model, it always can help increase the precision and F1 score in some way. But when adding the PDG and DFG, it has a big increase, as you can see in this part and this part. But adding the attention, they will not contribute a lot on the precision and the F1 score increase, but they can keep the recall, to keep the recall not reduced a lot. So by adding all these factors together, as you can see in the most right part, the gray line means the F1 score. Our model can get the best result by adding all these factors. So from this graph, we can have a clear idea that the program dependency graph can contribute most on the performance of our final model. So which means the global context is really useful in the bug detection problem. And here are some examples for the bugs detected by our model. For the first example is that, as you can see, this bug happens in 2 methods. This 2 method has a method call in method 2 to method 1, as you see the print. And then when the method 1 has a bug on its parameter, the method 2 also needs to be fixed because they already deleted 1 parameter. So if you only use the state-of-art approaches, it's really hard to find this kind of bugs. But because our approach uses graphs to find a relationship between different statements and methods, so our approach can catch this kind of bug easily. And then there is the other example of the bug detected by our approach. This bug happens in 2 versions, the 0.2 version and 0.8 version. This 2 version shows that there used to be a bug happens in the line 3 in the version 0.2. It changed a single line to the if statement. And in the next version 0.8, this statement is has been found that it's not in the right place, so it needs to be moved down. So in this way, we can see that if there is a previous bug information, our model can detect the bug more easier. So in our approach, as I said, I added a weight on the buggy path when doing the training. So when doing the prediction, the added weight can help us to detect the new bugs in new version easily than other state-of-art bug detection approaches. Then I can make a summary for our whole presentation. So for the first part, I talk about the three types of automated bug detection types and their limitation. We know that they often only consider one method. They often only consider some existing rules, existing type of bugs. So to solve this limitation, we come up with our approach. Our approach includes 3 steps. The step 1 and 2 are both the code representation part. And only the last step is very simple, is to do the bug detection. So we can see that our approach contributes a lot on the code representation way. And then we compare our results with other state-of-art approaches. Then all these results showing that our approach can work better than on both the bug detection approach ways and also on the code representation ways. So as a conclusion, our bug detection approach use program dependency graph and data flow graph to catch the global context, which is the relationship between the methods. And we use the long path to represent methods instead of using the ST directly, which is a better way to represent the code content and the code structure. And also, we add weights to specialize our model for the bug detection problem. And for the future work, we would like to test our model on different programming languages because in our model, in fact, there is not a very specific limitation on which programming language we are dealing with. So for now, we're only dealing with Java, but we think it's also useful for Python or C++ or some other programming languages. The other future work is that we want to do the statement level bug detection in the future. For now, we only can report which method is buggy, but for the future, we want to specifically telling the developer which statement is buggy or not. And then in the end, we want to do a fine-grained bug classification when we do the bug detection with the bug types, and the bug detection tool can help us, can help developers to have a clear understanding about which type of bug has been detected, how to fix them. So that's all about my presentation. Thank you for your listening. Next question.
Hi, thanks for the talk.
Thank you.
I have 2 questions. One is about the comparison with the existing bug detection tools. So if I understand it correctly, your tool is predicting whether an entire method contains a bug or not, right?
Yes.
And the existing tools are more fine-grained. They point at a particular line and tell you that this line seems to have this kind of bug.
Yeah.
So how did you compare? Did you run the existing tools, and whenever they reported some kind of bug in some line of a method, you counted this as a bug detected, or?
Yes. When we compare with the state-of-art bug detection approaches, if they detect, even they detect the other line, maybe in this method, we also regard they detect correctly because we compare in the method level. We want to be fair. Yeah.
All right. Okay. And then the second question about the comparison with debug. So debug is implemented for JavaScript. How did you run it on Java code?
Oh, we do some modification on that to make it run on the Java. But I don't think it's because we directly use their model structure and their ideas, but we just implement it ourselves to do that.
Did you retrain it on Java code?
Yes.
All right.
We train on the same data set with what we use.
Cool. Okay. Yeah, we should talk more later. Thanks.
Thank you.
I have a question actually on the experimental results. I was
Sure.
wondering the bugs that the other tools were detecting that yours didn't. Did you inspect them to see how come your tool was not able to do it? Was it the machine learning component, or was the approach based on the graph?
Yes, in fact we manually study the bugs that are covered by both our approach and their approach, and also we study the bugs that our approach can detect but they cannot. So in the specific learning on that one, we're showing that many bugs that happens in multi-method our approach can detect, but their baselines cannot, because they do not consider the relationship about that. So that's showing that considering the global context is useful in bug detection.
Okay. Any other question? Okay, let's thank the speaker again.
Thank you.
Working? Okay, yeah. So we move to the third presentation.